Welcome back. In this video we are going to look at something called the linearization theorem. And the linearization theorem allows us to look at nonlinear equations and begin to think about them as if they were their linear counterparts. So many real-world systems of differential equations are nonlinear. This means they do not allow us to use the eigenvalue-eigenvector approach to finding solutions. As a matter of fact, many of these nonlinear systems are even unsolvable. But not all is lost, because a nonlinear system tends to have more than one equilibrium point, and one of them is not always 0, 0, as is the case for a linear system. These equilibrium points, though, tend to have similar classifications. So sink, source, saddle, spiral sink, spiral source, and center. They look very similar a lot of times. And the ability to classify them as one of these will allow us to understand how the trajectory of an initial condition may take it towards certain equilibrium points and repel it from others. So before we get into this theorem, let's go ahead and consider a nonlinear system. This is the or a variation of the Lotka-Volterra model for competing species. And for fun, let's just say that X represents the number of zombies and Y represents the number of werewolves within a particular region. And the question that we should ask ourselves, first of all, is what do we notice about their interaction with and without the presence of the other? So to kind of make sense of this, this is called a competitive model. And I picked two species, or two imaginary species, that are competitive in the sense that they both seem to go after human flesh, but they do not eat each other. However, we could probably argue that the overabundance of one could lead to the decimation of the other, just by virtue of the fact that perhaps one is consuming the source of food for both of them. So first of all, one thing that we should notice is that if there's 0 of either of the two species, then that's going to result in, first of all, complete extinction of one of the species, right? So if x were to equal 0, then we would see that dx dt would reduce to 0, which makes sense, because if there are no zombies, we would expect none to be recreated. And similarly, if x is 0, that means dy dt, the second equation, the second term goes away, and you end up with 3y times 1 minus y over 3. Now this system here is one that has this equation here is one that has an equilibrium point at y equals 0 and at y equals 3. And so at y equals 0 and y equals 3, if we were to look at this over time, we would see kind of this logistic curve, and the population would approach the carrying capacity. So that would be without the presence of werewolves. Of course, we wouldn't expect them to grow indefinitely, because they also need to have a food source, and they don't want to dupe themselves. So now when y is equal to 0 and there are 0 werewolves, then dx dt becomes logistic. We see that the second term here goes away, and we're left with 2x times 1 minus x over 2. And so that's again going to be a logistic growth, but in this case, rather than to have 0 and 3 as equilibrium points, unfortunately you can't quite have as many werewolves. They're a little bit more, have a higher appetite, and probably consume more per werewolf. But of course, if y equals 0, we see that the second equation clears out, and we're left with dy dt equals 0, which makes sense. If there are no werewolves, then there will not be any. There will not become any. And then we wanted to ask how these two interacted. Well, first of all, we see that in the absence of the other, they both do just fine. But in the presence of one another, we see that we have this subtraction term here and here. And that subtraction term, or the size of it, is based on the sizes of the two populations. So if x is really large and y is really large, then the product is going to be really large. And if the product is really large, then that's going to subtract or create a big negative contribution to dx dt. So it's the interaction, the fact that if these two beasts are in too close of proximity, their interaction actually leads to destruction of both species. In the case of the werewolves, the presence of the zombie is more detrimental than for the zombies in the presence of the werewolves, because of this factor of 2 here. So it's doubly detrimental to, the interaction is doubly detrimental to the werewolves as it is to the zombies. So this is a competing species. We see that a high interaction rate actually is bad for both of them. And that you could see this where you have predator-predator situations or prey-prey situations, as opposed to predator, one being the predator and the other being the prey. So interesting model here, one that we want to better understand. And of course, this is in realistic terms used to model interactions between any two competing species in an environment. So if we consider the phase plane of this nonlinear system, and recall it's nonlinear because of the interaction terms here. This is what makes it nonlinear, is these two terms here. You have the product of dependent variables. Although it's not like saying x squared, it's two dependent variables multiplied together. So it is as if we're kind of squaring a dependent variable in a way. So the phase plane, as we look at this, we notice that it's pretty erratic. It's kind of hard to predict. It doesn't look like our linear systems. We see that over in the first quadrant, it looks like some solutions maybe, kind of curve in this way. Looks like here they come in this way, here they come straight down. But then over in this quadrant, it gets really crazy. It's almost like there's some sort of looping structure here. And out here, the solutions seem to veer out that way and maybe veer downwards. And here again, they kind of loop. So it's a very chaotic looking system. And that's troubling because in order for us to have a good sense of what's going on, we need some sort of tools with which we can better understand why what's happening is happening. So let's also take this side road and say, let's look at the equilibrium points of this system and see if somehow that allows us to see anything. Before we get at that though, let's go ahead and pull up this phase plane and play around with it a little bit. So recall this is our grapher app, and I just have the two differential equations input in here. Dx dt equals 2x times quantity 1 minus x over 2 minus xy, and dy dt similar. Independent variable is t. And here we're just looking at from time 0 to time 10. You can always change that if you want, and we can move the initial condition around the phase plane. Now the other thing that I want to ensure is that I'm going to choose RK4 system from here. That's the most precise of the methods available, and change the step size to 0.01, otherwise the trajectories look kind of square. So you'll see what I mean. If I change that to 1, for instance, you're going to see something that's remarkably, well, in this case, we don't see anything at all. So let's try 0.1 and see if that will give us a better representation. So here are these trajectories just kind of look very line-ish. And by setting the step size to be smaller increments, we'll have, instead of having 1 line here, we'll have 10 lines if we make the step size 0.01, so it looks more smooth. So you can see that depending on where I click the initial condition, in here we kind of saw these loops. And you can look at, so here we have the x-axis and here we have the y-axis. And then this, of course, sketches, here we have y versus time on the right. And you can see what y does for that initial condition. Y kind of hops up from a small positive value, hops way up here, and then the y value starts to descend back down. And it looks like it flattens out. It goes to some sort of point here and then just sort of stops. And it seems like all these initial conditions seem to do that. They come to this point and then just sort of flatten out. Already I'm beginning to think that there's an equilibrium point right there because I see that the population stops growing. And the same thing for the x population. We see that initially x is negative and x becomes more negative. It moves to the left, so this drops down until about here, at which point the x values start to approach 0 again. And so it looks like 0 is an equilibrium point. Here, if I kind of cursor over that, it looks like right around y equals 3 and x equals 0. So this looks like it might be the point around 0, 3, which looking at the coordinates here, yeah, it looks like x is about 0 and y is about 3. Now over here, depending on where I click, here it looks like certain trajectories are going straight to this point here, which looks like y is descending to 0, and x looks like it is hitting about 2 or so, right around 2 as time approaches infinity. But then as I move this initial condition, watch what happens. after a certain point, wow, look at that trajectory. Now that trajectory goes to that same thing that we were calling the equilibrium point. The x value over time descends to 0. The y value seems to now ascend to 3. And then things get even chaotic in here. They seem to be going to that same equilibrium point right there, 2, 0, and out here just a very different behavior. So we're going to do two things. One, we're going to try to analyze the equilibrium points and understand whether they attract or repel solutions. And then in the next lesson after this, we'll get into how do we understand or break up this phase plane into more manageable chunks. So let's go back and do some investigation. So if we did go ahead and compute the equilibrium points, remember for a system that means dx dt and dy dt are simultaneously 0, and we solve for both x and y using a solver like Wolfram Alpha. You can certainly try to do this by hand, but it's not going to be a lot of fun, and a computer can do this much faster. So we actually get 4 equilibrium points. And if you notice the very first one, which is the equilibrium point 0, 3, that was the point that we were seeing some of these solutions converge to. So 0, 3 was like this guy right around here. That point 0, 3 is where some of the solutions were going. And for this other guy here, 2, 0, it also looked like some of the solutions were going to that point, 2, 0. And 2, 0 was this point right over here somewhere, right about there. That's the position 2, 0. So when x is 2, y is 0, when there are 2, whatever, million zombies or 2 units of zombies and 0 units of werewolves, there will be no change in either population. When there are 0 zombies and 3 werewolves, there will be no change in either population. When they're both at 1, they seem to coexist happily, and they both stay out that population size. And of course, when they're both at 0, that makes sense. In this case, 0, 0 is an equilibrium point, because if there's an absence of both predators, then there is not going to be any growth, unfortunately. Or fortunately, depending on how you want to look at it. So if we look back at the phase plane, we see that some trajectories end up at some of the equilibrium points. There must be some explanation. If we zoom in to look locally in the neighborhood of these equilibrium points, we might see something familiar. So let's just focus on 0, 3 and 2, 0 for a moment. Go back to the phase plane. So for 0, 3, I want to set my y value to be right around 3. So I'm going to go from about 2.99 on my y-axis to about 3.01. And then I'm going to, for x, be right around 0. So negative 0.01, so just slightly to the left of 0, to 0.01, slightly to the right of 0. And what I notice right in the center, where I have the point 0.03 right around here, is that look what happens to these trajectories. These trajectories, we seem to have some sort of straight line solution here, and it looks like another straight line solution here. You can see the arrows pointing directly inwards, and along this straight line they're also pointing directly inwards. So we might want to begin classifying this and thinking about this as a linear system. This looks a whole lot like a sink. This point 0.3 looks a whole lot like a sink. And if we look at right around the next coordinate, or the next point, and changing this right around to the point 2, 0, so I'm going to have my x value go from a little bit less than x equals 2, 1.99, to about 2.01. And this, we want y to be at 0, so let's go negative 0.01 up to 0.01 and see what happens. And boy, oh boy, it looks like this also seems to act like a sink. And in fact, if we start to look at these different trajectories, we see that all of the solutions seem to curve into the point 2, 0, the ones that are at least local to it. So the reason we're looking at just a small projection on either side is because we're only going to make an argument that this equilibrium point behaves like a linear system whenever you are within the neighborhood. Okay, so it's sort of like if somebody's having a loud party and they're blasting music, you're not going to be able to hear that music if you're 4, 5, 6 blocks away. I'm assuming it's not that loud, but as soon as you get to within that neighborhood, a couple doors down, you're going to be able to hear it, right? And then you get super close to the house that's having the party, you're really going to be able to hear it. So we're doing kind of that analogy here, where as long as we're really looking at a region very, very close to the equilibrium point, then locally we're going to make the argument that that equilibrium point behaves like one of our linear systems. And so again, we see that here's a straight line solution, in this case along the x-axis, and the other straight line solution seems to be going at a diagonal. And this also looks like all the arrows are pointing inwards, so we'd classify this as a sink as well. We had another equilibrium point right at 1, 1, so let's also look within the neighborhood of the point 1, 1. So remember, neighborhood just means slightly to the left, slightly to the right. So 0.99 to say 1.01. And then we'll do the same thing here. We'll go from 0.99 to 1.01. And wow, doesn't that look a lot like a linear system? In this case, it looks like a saddle. We see that there appears to be a straight line going from diagonal bottom left to top right, as well as from top left to bottom right. And it looks like here the vectors are pointing inwards towards the equilibrium point 1, 1. But here along this straight line, they're pointing outwards. So it appears that the equilibrium point 1, 1 is going to be a saddle. And again, we're just within the neighborhood. As soon as we start to zoom out more and more, we start to see that very chaotic and unpredictable behavior that we saw in the original phase plane. But this begs an interesting question. How do we mathematically quantify each of the equilibrium points in the event that we couldn't look at them all, or perhaps in the event that we had more than 2 differential equations and we maybe had a system of 3 differential equations? It'd be a lot harder to try to look at all the equilibrium points in 3 dimensions. So we have a theorem for this that's called the linearization theorem, and we'll take a look at that in a moment. And just some remarks here before we introduce the theorem. This was our original equilibrium point 0,3 that we looked at, and I've just sort of superimposed the 2 straight lines that represent the eigenvectors for the linear system right around that point. And we see that that is looks like a sink for a linear system. This was our where we were looking at the point x equals 2, y equals 0 right there. And we again kind of saw that there was a straight line solution there. Let me change colors here, make that black. So we see how that was a straight line solution about there, and that there's also a straight line solution along the diagonal right about there. We'll call that good. There we go. And so we again saw that in this circumstance, it appeared that all along the straight line solutions, all the vectors point inwards. And so that point right there, which is 2, 0, 2, 0, looks like a sink as well. Here is right around the point 1, 1. So 1, 1 is right inside of there. This one looked like a saddle. And so let me go ahead and kind of sketch in those straight line solutions from the linear system. And there's one right about there. I know that's not perfect, but good enough. And so we see that the vectors point in on this straight line solution here, but they point outwards here. And so this equilibrium point at 1, 1, 1, 1 looks like a saddle point. Okay, and again, what we mean here is locally within the neighborhood. It's only whenever you look at the phase plane very, very close surrounding that equilibrium point that we observe this happening. Because remember, when we zoom out, we see this. And you wouldn't be able to tell based upon this that what's going on near 0, 3 and 2, 0. But as we begin to zoom in and drive into that neighborhood, we can hear the music. We can hear the sounds of this particular behavior. I've also taken the liberty here to plot the point 0, 0, the equilibrium point, which is You can see we have two straight line solutions in this case once again, and all of those vectors point outwards. So along here, they point outwards. And also, one of the interesting things to note is that none of our trajectories that we just sort of clicked in the phase plane on ever went to 1, 1. Well, that makes sense because 1, 1, it acts as sort of an attractor and a repeller at the same time. So some solutions will near 1, 1, but they'll never actually get to 1, 1 because the vectors immediately push it away, the ones that are pointing outwards. In this case, we can never get to 0, 0 unless we start off at 0, 0 because all of the trajectories will kick it away. So 0, 0 acts like a repeller, which is why we didn't see any of the trajectories move to 0, 0. And remember, this looks like a source. Once again, we want to say locally because we zoom out, we don't see that anymore. Perfect. So we've kind of visually classified these, and I'll say locally here as well. We've visually classified all of these, but again, we want to have some mathematical way to do it because mathematics gives us more of an objective viewpoint from which to take a look. So the linearization theorem at first looks kind of odd, and we'll give it some insight later on, but let's see how it works first. So let y naught, so that's kind of a vector, be an equilibrium point. So just define the equilibrium point y naught to be the equilibrium point, the ordered pair x0, y0. So it's just some point for the nonlinear system. dx dt equals f of xy, dy dt equals g of xy. It's Jacobian matrix, this is a definition. Jacobian matrix at the equilibrium point is the matrix with the partial derivatives. Now, we're calling dx dt f of xy. So when we say df dx, we're saying take the derivative of this function with respect to x. Take over here the derivative of that same function with respect to y. So this whole first row represents dx dt. So they're all going to relate to the original nonlinear dx dt. When we take these derivatives and evaluate them at the equilibrium point, what we're going to get is a set of constants that will represent a matrix full of 4 constants looking like a linear system. In the second row, that relates to dy dt, so that's going to be the derivative of g with respect to x, and the derivative of g with respect to y, and then we'll plug in the equilibrium point in question, and what that will give us is the 4 coefficients that we'll need to produce the linearized system. So basically, we're going to take our nonlinear system, we're going to reduce it to a linear system. So notice this looks like AY, but we call it JY. We do that because we don't want to make it seem as though our original system was linear to begin with. So we're basically linearizing it by computing this Jacobian matrix. We'll give a little bit of insight into this. It turns out it's pretty intuitive, but let's not do it now. Now this does have some restrictions. If the determinant of j is not 0, so this is the valid linearization as long as 2 things hold. The determinant of j is not 0, that is, this is the notational way to write it, and the eigenvalues of j are not purely imaginary. So for example, purely imaginary would be if I wrote 3i. But something that is not purely imaginary would be something like 2 plus 3i. So here you have a real part, a non-zero real part, and a imaginary part. We're not going to get into why this is specifically true here, but if these 2 conditions hold, then the solution curves of the nonlinear system near that equilibrium point behave in the same qualitative way as the solution curves of the linear system. We've already seen that that is the case from these 4 phase planes when we looked very close to our equilibrium points. Now we have a way of actually computing that linearized matrix. Once we have that linearized matrix, we can compute its eigenvalues, and we know just based on the eigenvalues whether that point will behave like a sink, source, spiral sink, spiral source, center, or saddle point. So first of all, when you compute the determinant of a matrix, So when you have four values like this, it's the product of the diagonals from top left to bottom right. So you see there's A times D minus the product of the diagonals from bottom left to top right, BC. So you have to check, make sure that's not equal to 0. As long as it's not, you're all set. The second thing that we need to just ensure that is that the eigenvalues are not purely imaginary. And that's when after we have verified that the determinant is not 0, that only at that point can we go and investigate and look at the eigenvalues themselves. So if you find out that the determinant is 0, you stop there. This theorem is not going to be useful. At that point, all you can really do is kind of do this type of analysis where you zoom in, if that is at all possible. So note one, the theorem is quite vague in what same qualitative way means. The implication is that the behavior of the linearized system is similar to, but not necessarily identical to, the non-linearized system for initial conditions near the equilibrium point. And then the second kind of question we want to ask is, what kind of equilibrium is disqualified by this theorem? Well, if you get a purely imaginary eigenvalue, that means that you're going to have 0 plus or minus hi. And if g is 0, then you get a center. If g equals 0, the equilibrium point is a center. Now, just because you get a 0 real part doesn't mean it can't be a center. It just means that if you get a 0 real part, the theorem cannot promise you anything. So let's go ahead and classify our equilibrium points for the zombie werewolf model. Here is our dx dt. Recall that this is called f of xy, and recall that this is g of xy. So in our first row of our Jacobian matrix, we're going to take the derivative of dx dt with respect to x, and then again with respect to y. So we're not going to do anything yet with the equilibrium points. Hold off on that. First, compute the Jacobian matrix as a function in terms of its functional form. So here we have, notice that this is our derivative of f with respect to x. So the derivative with respect to x of dx dt, and this right here is the derivative of x with respect to y. So derivative with respect to y of dx dt. We're using this partial notation. This is similar to saying df dx, and in fact you've heard me say df dx. And if you have not taken Calculus 3, don't worry about the difference. Ultimately, the reason we use this different notation instead of the lowercase d is because this implies that there's more than one input variable. There's an x and a y. In any case, we want to take the derivative of this with respect to x and the derivative of that same thing with respect to y. Now, dy dt, or g of xy, are the derivatives that are going to go into the second row. So this right here is the derivative of dy dt with respect to x. So there's dy dt, derivative with respect to x. Here is dg dy, that's the derivative of dy dt with respect to y. If you haven't taken Calculus 3 and you're viewing this and you're like, I don't know how to take partial derivatives, you can use Wolfram Alpha to find them. But the premise is kind of the same here. If you distributed the 2x, this would really become 2x minus x squared minus xy. The derivative of 2x with respect to x is 2. The derivative of x squared is 2x. Now the derivative of negative xy is actually going to equal y, because you're thinking about y as a constant when you're taking the derivative with respect to x. So it's sort of like when you took the derivative of, say, 3x in Calc 1, and you could factor out the 3 and just take the derivative of x. The derivative of x, you would get 3 times 1, or just 3. So you can actually factor out the y when you're taking a derivative, and then the derivative of x is 1, and so you end up with negative y times 1. But again, you can do this in Wolfram Alpha. To do it in Wolfram Alpha, you would just type in, like, for example, to get both of the partial derivatives of dx dt, you could just go in Wolfram Alpha, type in partial derivatives, then the function that you want, and it will spit out both the one with respect to x and the one with respect to y. So the derivative of this same function with respect to y, the derivative of the x terms is 0, and the derivative of negative xy is negative x. The derivative of dy dt with respect to x, well, this is all going to have a 0 derivative because it's all constant, and then the derivative of negative 2xy with respect to x will be negative 2y. And repeat that over here. The derivative of 3y times 1 is just 3. The derivative of 3y times y over 3 is the derivative of y squared, which is 2y, and the derivative of 2xy is 2x. So again, feel free to do this in Wolfram Alpha if you're not following along, and just note that you will be able to come up with these values. So here we have the symbolic Jacobian matrix. This is now the same matrix we're going to use for all 4 of these equilibrium points. So let's begin to classify. We can pick whichever one we want first. So classify. And let's start with the equilibrium point y0 equals, let's say, 0, 3. I think that's one of the ones we started with earlier on. So to do that, and because I know my Jacobian now, I can now simply plug in my coordinates and compute j of 0, 0. So j of 0, 0 is really just plugging in 0 for x, 0 for y. If I plug in 0 for x and y, I'll get 2, negative 0, negative 2 times 0, and 3 minus 0. So there is my Jacobian matrix, and now I just need to check the 2 conditions. Before I compute eigenvalues to classify this equilibrium point as a sink, source, saddle, spiral sink, spiral source, I first need to make sure, 1, the determinant of j0, 0. I need to make sure that this is not 0. So to find the determinant, it's 2 times 3 minus 0 times 0, which is going to give me 2 times 3 minus 0 times 0, which is 6. So clearly that's a non-zero eigenvalue. We're in good shape to proceed. Let's compute the eigenvalues. Voila, here they are. Lambda 1 equals 3, lambda 2 equals 2. It is not coincidental in this case that the eigenvalues are the same as the diagonal entries. Whenever you have a diagonal matrix like this where there are zeros above and or below the diagonal, then the eigenvalues are just going to be the values along the diagonal. But that's just a special case. So they're both positive. And if both eigenvalues are positive, that means that the point 0, 0, I said we were going to start with 0, 3, but we're looking at 0, 0 here. So let's just go ahead and change this to 0, 0. So 0, 0 we already classified. We said that this would end up being a source. And because both of our eigenvalues are positive, this does in fact, if we look at our schematic, our drawings of the different phase planes, this means 0, 0 is in fact a source since both eigenvalues are positive. So if I wanted to kind of sketch the picture of what's happening near 0, 0, I could do that. I could say, okay, here's 0, 0, and the eigenvectors are the axes, right? This axis here is, one of the eigenvectors, or the eigenvectors lies along this line, and then the other one's on 0, 1, which lies on this line. And both of the arrows point away, like this. And this is exactly what we saw in our picture from above when we looked at the local picture near 0, 0. There it is, right there. So this theorem does indeed seem to work. Now we repeat the same thing for the other guys. Same process, but just with the other equilibrium points. So let's classify, let's now do 0, 3. Let's look at 0, 3. Okay, so that means I have to go back to my Jacobian matrix and plug in 0 for x and 3 for y. So let's see what that will be. So if I plug in 0 for x, that'll be 2 minus 3 is negative 1, 0 equals negative 1, 0. And then let's look at the second row. When x is 0, y is 3, negative 6. And so let's write that down. Negative 6. And then the last one here is going to be, let's see, 0, 3. So the x is 0, y is 3. This will be 3 minus 6, which is negative 3. Again, I'll just check the determinant. Oh, and up here, the second condition, we needed to check just to make sure our eigenvalues weren't purely imaginary. So not purely imaginary. This second check you only do as long as the determinant is not 0. If the determinant is 0, you don't compute the eigenvalues. At that point, you want to look locally at the equilibrium point itself. Okay, so one determinant of J03 is the product of the diagonals from top left to bottom right, which is negative 1 times negative 3, minus negative 6 times 0, which is equal to positive 3, so that passes. We can now compute the eigenvalues and eigenvectors. For this Jacobian matrix, we will get eigenvalues of negative 1 and lambda 2 equals negative 3. And so these are not purely imaginary, which is our second check that we've passed. So there's actually not an imaginary component at all. They're not complex eigenvalues. And so what that means, if both eigenvalues are negative, then 0, 3 acts like a sink, since both eigenvalues are negative. And that matches our picture that we looked at locally near the point 0, 3 in the phase plane right up here. 0, 3, we saw that had negative eigenvalues, must have had negative eigenvalues. And by the way, I didn't show the eigenvectors, but if you calculated the eigenvectors using Wolfram alpha, you would notice that one of them would lie straight up and down, and the other one would lie on this diagonal. So you could even sketch this phase portrait pretty accurately near 0, 3. And let's go ahead and do the last two. So 2, 0 is another one of them. So 2, 0. So y0 equals 2, 0. So compute the Jacobian matrix again. So J evaluated when x is 2, y is 0 is going to be, let's go up to our formula back here. Probably should just go ahead and copy that. And so here it is. And so we see that when x is 2 and y is 0, we're going to get 2 minus 4, which is negative 2. And here we'll get negative x, which is negative 2. 0, and here we'll get 3 minus 4 is negative 1. So determinant of J at 2, 0 is going to be negative 2 times negative 1, which is positive 2, minus 0 times negative 2, which is 0. So we get a determinant that is not 0, and we can proceed. The eigenvalues that we would get for this would be lambda 1 equals negative 2, and lambda 2 equals negative 1. So, because again they're both negative, 2, 0 acts like a sink. And that is so cool because when we witnessed that back up here, we saw that in fact 2, 0 was a sink, and that was some of the initial conditions that we picked would go to 2, 0 and the others would go to 0, 3. And this is helping to explain why. Now 1, 1, that's our last equilibrium point that we want to classify, and without a doubt we're going to end up finding out that this is going to be a saddle. So J of 1, 1 is equal to, let's go ahead and grab this over here so we have it handy. And okay, so there we go, there's our J matrix. And so we're going to find that when we put in 1 for both x and y, here we'll get 2 minus 1, which is negative 1, negative 1, negative 2, and 3 minus 4, which is negative 1. So here we notice that we get one negative eigenvalue and one positive eigenvalue, which means that, oh, and we didn't check our determinant of J11 is going to equal -1 times -1, which is 1, minus 2, which is -1. So that's a positive check. And these are not purely imaginary, so that's good. One's negative, one's positive, so near the point 1, 1. So let's just say that the intersection of these two axes, we'll just say that's the point 1, 1. And so we have two eigenvectors, 0.7, 1, which will look something like this, 0.7, 1. And there'll be, should be a straight line solution going through those points. So let's go ahead and move this just slightly. There we go. Good enough. And same thing on the other side, -0.7, 1. We'll have another straight line solution coming in slightly like that. And so because along the V1, this guy going from bottom left to top right, the eigenvalue is negative, those straight line solutions are going to point in, and since along this eigenvector V2 we have a positive eigenvalue, we'll get trajectories that should kind of look like this around that point. And so we have a saddle, 1, 1 is a saddle, and the reason I went to go ahead and draw this one is just to make that complete illustration that that's going to look very, very much like the picture for the 1, 1 equilibrium point. You can see that we hit it spot on. So I think this video is getting a little lengthy. I think in perhaps a separate one at some point I may get into the explanation for why this is true. But essentially, when you look at this formula and you try to explore this a little bit, when we take the derivative of something, we're getting a slope. So in this case, to give you just a little bit of intuition, df dx is the same thing as taking the derivative with respect to x of dx dt. And we're looking at this near our equilibrium point x naught, y naught. So what this actually tells me is, how does the slope change? How does dx dt change near x naught, y naught? And so, for example, if the slope is changing by 4, then that allows me to linearize that coefficient to say the slope dx dt is changing by 4 units when you're very, very close to that equilibrium point. Df dy is the same thing as saying, how is the slope when you change y a little bit near your equilibrium point, how does dx dt change? And so again, you're going to get a numerical value that represents the slope near the equilibrium point. And that's these are both for dx dt. We do the same thing for dy dt, and this just tells us or allows us to kind of see, what is happening to these slopes very, very close to that equilibrium point. And that's why we need to basically identify a very local picture. So if we're looking at 0, 0, then having a neighborhood that is very, very close, -0.01 to 0.01 and -0.01 to 0.01, these values just tell us where the slope vectors are pointing right around that equilibrium point. So there's just a little bit of quick intuition without getting into more of the theory. And that's it for the linearization theorem. Next time we'll look at null-Klein analysis. And what null-Klein analysis will allow us to do is to look at the whole nonlinear phase plane and be able to explain what's going on.